So the last lesson segment that we have in this sort of chapter on integration is the idea of improper integrals. And when we talk about an integral being improper, there are effectively three things that cause an integral to be improper. The first is that an integral can have an infinite bound, and this is something we haven't dealt with before. But if you have a problem that's asking you to take the integral from 0 to infinity of f of x dx, then this is an improper integral. We can still do it, but it's improper because it has an infinite bound. The second thing that can cause it is that one of the bounds can actually be a vertical asymptote. So suppose you had an integral that was going from 0 to 4 of 1 over x dx. Right? We know just by looking at it that 1 over x has a vertical asymptote at 0. So anytime that a vertical asymptote is one of the two bounds, that's another reason for an integral to be improper. And the third cause for an integral to be improper is that you can have a vertical asymptote that's actually within the bounds of integration. So whereas this one started at an asymptote and went away from it, we could have something like the integral from -1 to 1 of 1 over x dx. Right, so again, we recognize this has an asymptote at 0, and 0 is right in between these two things. Previously, we haven't had any way of dealing with these sorts of things, and in this sequence of lessons, we're actually going to talk about how we do that. So when we talk about improper integrals, there are actually singly and doubly improper integrals. In other words, singly improper meaning that there's one thing wrong with them, doubly meaning there's effectively two things wrong with them. And so the first type that we're going to talk about is an integral that has an infinite bound. So if you have an integral that has one of its bounds being infinite, our strategy is simply this. We're just going to express the infinite bound using a limit, then we'll find the antiderivative, and then we'll evaluate the limit. It's going to be as simple as that. It really just means we set up a limit that's approaching infinity, and then evaluate that integral. I have an example or two of that, so we'll take a look at those now. So here we go. I'd like us to evaluate this integral. So as mentioned in our strategy, step 1 is to express this infinite bound using a limit. So I'm going to say, okay, that infinity, I know I'm not allowed to plug in infinity, so let's write the limit as a approaches infinity of the integral from 0 to a of x squared e to the negative x dx. So now step 2 is to actually do that antiderivative. So this is where I'd like you to sort of pause the video and think back on the lessons we've done in this chapter, think about how we're going to do this integral, and take a minute to do that integral. So this should be tabular integration. We can do our derivatives on one side and our integrals on the other. I'll take the derivatives of x squared and the integrals of e to the negative x. So it'll give me 2x, 2, and 0. Make that negative, so this will be negative e to the negative x, e to the negative x, and negative e to the negative x, and then we're supposed to multiply diagonally. Hopefully you remember that that's how tabular works. So now I have the limit as a approaches infinity of this integral, negative x squared e to the negative x, minus 2x e to the negative x, minus 2 e to the negative x, and I'm evaluating from 0 up to a. So great, now we're taking the limit as a approaches infinity of, and we're going to sort of write these things out plugging in the a, negative a squared over e to the a, minus 2a over e to the a, minus 2 over e to the a, minus, and now when I plug in 0 to these things, I'm going to get 0, minus 0, minus 2. Right? So now I have to do these limits, and you'll notice that this limit as a approaches infinity gives me infinity over infinity, infinity over infinity, 2 over infinity. This is basically 3 separate examples of L'Hopital's rule, right? So we can sort of, either do L'Hopital's rule or sort of imagine doing L'Hopital's rule. In this case, we can imagine when you keep taking the derivative at the bottom, it's going to keep giving you e to the a, which is infinity. On the top, your first derivative is 2a, the next one after that is 2, you're going to end up getting to the point where you have 2 over e to the a. Same thing here. Long story short, when you do this limit, and I'm hoping that you guys can sort of see this without sort of seeing all the work that's going into it, we can tell this first thing is going to be 0, this next one's also going to be 0. In fact, all of these things turn into 0. All that's left is this minus negative 2 at the end, which means our limit, and therefore our improper integral, ends up being 2. Right? So the reason we did L'Hopital's rule right before this is that a lot of times these improper integral problems sort of require you to have a working knowledge of L'Hopital's rule and how to work it out. The second type of singly improper integral that we'll deal with is an integral that has a vertical asymptote as one of its bounds. Our strategy is actually very, very similar. We express the asymptotic bound using a limit, we find the antiderivative, and then we evaluate the limit. It's really, really not a big deal. Right? So here I have the integral from 2 to 10 of 4 over x minus 2. Hopefully you can tell from the x minus 2 in the denominator that this function will have a vertical asymptote at 2, which means I'm not going to be allowed to plug in 2. What I'll have to do instead is write the limit as x approaches 2, and this is potentially important. It's not a double-sided limit. If I'm going from 2 to 10, I'm approaching 2 from the right. And I know that seems strange because it's actually the left bound, but if you're thinking about the interval of numbers between 2 and 10, if you were trying to sort of fill in this entire thing, you'd plug in 10, and then we would have to approach 2 from the right in order to get to it, like while staying on this interval. Right? So I'm going to have that limit. I'm sorry, and it won't be the limit as x approaches 2. It'll be the limit as a approaches 2 or b approaches 2, some constant. So from a to 10 of 4 over x minus 2 dx. From here, we should be able, you guys should be able to do this integral, plug in a, do the limit, and work out what the answer is. So pause the video, try that out, see what you end up with. So I'm getting that this is the limit as a approaches 2 from the right of 4 times the natural log of x minus 2, evaluated from a to 10. Again, the limit as a approaches 2 from the right of 4 times the natural log of 8, 10 minus 2, minus 4 times the natural log of a minus 2. And at this point, remember we always evaluate our limits by attempting to evaluate for the value that's given. So when I try to plug in 2 here, I'm effectively going to end up with 4 natural log 8 minus 4 natural log 0. And that's not really allowed, but what happens as natural log approaches 0? This thing basically approaches negative infinity. So I'm sort of in a position where I have 4 natural log 8 minus negative infinity, and all this is in red because it's not stuff you would really write, but what we notice when this happens is we can tell that this integral diverges. And what does it mean if an integral diverges? It means that that integral doesn't add up to something. It means when you were trying to find the area under this curve, it was an infinite area, right? And we can even sort of picture that when we come back to this problem. This problem was asking us to, imagine what that function looks like. It has an asymptote at 2. We have this function, and they wanted the area between 2 and 10. They want this area. Well, because there's an asymptote here, it turns out that area is actually infinite. What's exciting about these lessons is that, like we saw in the previous example, they're not always infinite. They don't always diverge. Sometimes they do work out. This, again, I wouldn't be surprised, is something that you have questions about. So write down your questions to ask them during class in terms of how that can work. I've got a couple more examples for us of this, so we'll go on and we'll do those now. So here's another example of an integral for us to evaluate. I'd like you to pause the video and sort of figure out what makes it improper, and then work through evaluating this improper integral. So the thing that makes this improper is the 5. That 5 is going to cause division by 0. It's a vertical asymptote. So I'm going to have to do the limit as a approaches 5 from the right of the integral from a to 6 of dx. Actually, I'm going to rewrite this integral. I'm going to call it x minus 5 to the negative 3/2 dx. That'll make it easier for me to actually do the integral. So we'll increase the power by 1, it'll be negative 1/2, and so we'll multiply that. So negative 2 times x minus 5 to the negative 1/2, evaluated from a to 6. So we have the limit as a approaches 5 from the right of negative 2 times 6 minus 5 to the negative 1/2 plus 2 times a minus 5 to the negative 1/2. This first term here works out really nicely. That's just negative 2. Then this other one, we have plus 2 over the square root of a plus 5. So what happens as a approaches 5 from the right? Right? As we approach 5, oops, I just mistyped that, right? This positive sign here should be a negative sign. What happens as a approaches 5 from the right? It means I'm plugging something barely bigger than 5 here. This is turning into 0 on the bottom. So this thing here is approaching infinity. this whole limit is approaching -2 plus infinity. So what is our conclusion about the fate of this integral? We conclude this integral diverges. Right, the area under this curve is turning out to be infinite, and so we are not going to be able to find out what the definite integral is. Here's one more example for us. Again, pause the video, decide what about it is improper, and then set up, how you're going to solve this improper integral, and then actually evaluate it. So the thing that's improper about this integral is that it has an infinite bound. It does have a vertical asymptote at 0, but 0 is not one of my bounds, nor is it between the bounds, so I'm not worried about it. All I have to worry about is the infinity that's up here as a bound. So I'm going to take the limit as a approaches infinity of the integral from e to a of ln x over x dx. Seems to be the best way through this is to do a u substitution. U equals ln x, so du is 1 over x dx, and that means dx is x du. When we go back to plug this in, the limit as a approaches infinity of the integral, and I'm not even going to put bounds on it, the integral of u over x times x du. Surprise, surprise, these x's divide out to 1. And my simplified integral becomes the limit as a approaches infinity of, let's see, this integral up here is just going to be u du, so we can tell that's going to be 1/2 u squared. So I'm going to go 1/2 ln x squared. And now that it's back in terms of x, I can put my old bounds back on it, e and a. So now we have the limit as a approaches infinity of 1/2 ln a squared minus 1/2 ln e squared. So I have the limit as a approaches infinity of 1/2 ln a squared minus 1/2, because the natural log of b is 1. So now we've just got to think about this limit. Right? We have to think, as a approaches infinity, what happens to the natural log of a? As a approaches infinity, natural log a just gets larger and larger. If you think about the graph of natural log a, looks like that. So as a gets larger, the natural log gets larger, and so when I have something larger and larger that's getting squared, that's going to keep getting larger and larger and larger. So this integral also diverges. So I think of our 4 examples, we had 3 that diverged and 1 that did not. That doesn't mean that 75% of them are going to diverge. It just means some are and some aren't. We're going to have to work through them to figure out whether or not they converge to a number or whether they diverge and add up to infinity.